This video gets you started using Property Specification Language assertions. Imagine a very simple bus protocol that requires 7 signals. The environment asserts the reset signal to reset the arbiter state. The devices assert their request signal to request access to the bus. The arbiter asserts a grant signal to grant a device access to the bus while rotating priority in a round-robin manner. The granted device asserts the data-ready signal while it has placed data on the bus. The granted device asserts the done signal in the last cycle of its bus access. And the arbiter asserts the busy signal with the grant signal and otherwise removes it in the cycle after done. Here is an example of two-word data transfers. On the first cycle, the arbiter grants the device 0 request and raises the busy signal. On the second cycle, device 0 lowers its request, drives first data onto the bus, and raises its data-ready signal. Device 1 coincidentally makes a request that the arbiter cannot yet grant. On the third cycle, device 0 drives second data onto the bus, raises its done signal, and makes another request that the arbiter cannot yet grant. On the fourth cycle, device 0 lowers its done signal and its data-ready signal, and removes its data from the bus. The arbiter grants the device 1 request and maintains the busy signal. On the fifth cycle, device 1 lowers its request, drives first data onto the bus, and raises its data-ready signal. On the sixth cycle, device 1 drives second data onto the bus and raises its done signal. On the seventh cycle, device 1 lowers its done signal and its data-ready signal, and removes its data from the bus. The arbiter grants the device 0 request and maintains the busy signal. On the eighth cycle, device 0 starts the second bus access. An assertion is a statement that a design property is true. That is, that it exhibits some particular behavior, and is also a directive to verification tools to verify that the property is true. But I get ahead of myself. Let's instead start at the bottom with, what is a Boolean? A Boolean is an expression of design states and/or numerical literals that has a Boolean true or false value. What is a sequence? A sequence is an expression of successive Boolean expressions evaluated over one or more cycles, usually clock edges. You compose sequences from Booleans and other already composed sequences. You cover a sequence. That answers the question, did the sequence occur? What is a property? A property is typically an expression of successive sequences, chained by implication. You can typically express a property as an if, then, else expression. You compose properties from Booleans and already composed sequences and other already composed properties. You assert a property. That answers the question, does the property hold? That is, does the design exhibit that behavior? Let's assert that a request implies an eventual grant. A property specification language directive is an optionally labeled verification directive. Among the defined verification directives is the assert directive. An assert directive is in order the assert keyword, the property to assert, and an optional report clause, reporting a string upon each assertion failure. Following this syntax, we label the assertion statement, provide a property placeholder, and report an appropriate message. The property specification language defines three kinds of properties. We have interest in only the foundation language properties. Henceforth, when I use the property word, assume that I mean a foundation language property. The property specification language defines many property expressions. The ones we will use here are the property instance, a clocked property, an aborted property, and an always property. The assimilator evaluates the property on the simulation cycles at which the clock context is true. The clock context is by default true, which means that absent a clock context, the assimilator evaluates the property, conceptually at least, on every simulation cycle. For performance reasons, simulators evaluate unclocked properties on only those cycles at which an input to the property changes. Henceforth, when I use the cycle word, assume that I mean the simulation cycles in which the clock context is true. The abort operator specifies a condition that removes any obligation for the operand property to hold. This version is an asynchronous abort. That is, it aborts the property asynchronously of the clock context. The always operator specifies that its operand property holds for the current and future cycles. Absent the always operator, assertion of a property asserts only that it holds in the current simulation cycle. Precedence is important. I have listed these operators in their order of precedence. Anywhere that precedence is unclear, be sure to force precedence by grouping property expressions with parentheses. Following this syntax, we provide the always operator, instantiate the request grant property, and provide it with the request 0 and grant 0 arguments. Abort the attempt upon reset, and clock the property. Now let's go ahead to actually define that instantiated property. The property declaration syntax is in order: the property keyword, a property type identifier, an optional formal parameter list, the HDL specific definition symbol, and the property expression. Following this syntax, we declare the request grant property, providing input arguments for the request and grant signals. The property specification language defines many property expression forms. One of those forms is sequence implication. This form is next cycle implication. The cycle in which the left operand sequence behavior completes requires the right operand property behavior to start in the next cycle and complete in whatever is the required cycle of completion. Failure of the left operand to complete is a vacuous pass. The attempt vacated. It went away. Failure of the right operand to complete is failure of the attempt. Following this syntax, we insert an antecedent left operand sequence placeholder, a next cycle implication operator, and a consequent right operand property placeholder. Something occurring implies that something else must follow. The Property Specification Language defines many sequence expression forms. One of those forms is a braced sequential extended regular expression. The sequential extended regular expression is an intermediate syntax from which you construct sequences. In the Property Specification Language, most discussion of sequences is really discussion about sequential extended regular expressions. A sequential extended regular expression can be many things, among them just a Boolean. Following this syntax, we replace the antecedent left operand sequence placeholder with a Boolean Property Specification Language function. This function is true in the cycle in which its argument is 1 and was 0 in the previous cycle. That is, it rose. We use this function instead of the signal itself because a device typically maintains its request until granted. We want only the first of those cycles to start an attempt on the consequent right operand property. Request rising implies that something else must follow. The Property Specification Language defines many property expression forms. One of these forms is a sequence. A sequence is one kind of property. You can optionally make the sequence strong. We will look at weak and strong properties and sequences in just a little bit. Likewise, as you have previously seen, a braced sequential extended regular expression is one kind of sequence. One of the things that a sequential extended regular expression can be is a concatenation of two sequential extended regular expressions. Concatenation means that the left sequential extended regular expression operand completes, and in the next cycle, the right sequential extended regular expression operand commences. Following this syntax, we replace the consequent right operand property placeholder with a braced sequential extended regular expression concatenation. Request rising implies that something else must follow, and that something else ends with a grant. Another thing that a sequential extended regular expression can be is a compound sequential extended regular expression. If this is starting to look complicated, just think of these things as many pieces that go together to compose a sequence. Having several different names for the pieces is just a syntactical convention. A repeated sequential extended regular expression is one kind of compound sequential extended regular expression, and consecutive Boolean repetition is just one kind of repetition. The count can be any integral value between 0 and infinity, and if any count is what you want, then you can omit the count entirely. If the Boolean is the true value, then you can also omit the Boolean. Following this syntax, we replace that something else with any number of repetitions of something that is always true. Request rising implies that any number of cycles follow and then grant. You can accomplish exactly the same result with same cycle implication and a delay of at least 1. Does this solution have something wrong with it? It actually does, and unless you already knew it, well, you wouldn't know it. The sequence expressions are by default weak. That means that if an attempt of the property is ongoing and your simulation terminates for any reason, the simulator does not report a failure of that attempt. How is that a problem? We have stated that upon making a request, the grant can arrive in any cycle after that, including the cycle before infinity. Formal analysis tools can figure this out. Simulators must actually crunch those cycles. So, for simulators, time is necessarily finite. Simulators cannot fail this property because, who knows, maybe the cycle after simulation terminated is the cycle in which the grant would have come. So we have a conflict here. We want to verify the property, but we also want the simulator to not, upon termination, report a failure of an ongoing attempt. To verify the property, we could rewrite it as a strong property. If an attempt of a strong property is ongoing, and your simulation terminates for any reason, the simulator does report a failure of that attempt. To rewrite this as a strong property, you can make the consequent sequence strong, or you can just use the strong eventually property operator. This actually verifies the property, but now, if an attempt of the property is ongoing, and your simulation terminates for any reason, the simulator reports a failure of that attempt. Is this what you really want? To verify the property, we could keep it as a weak property, but put some upper limit on the eventually part. That limit can be the longest delay you can possibly stand before the grant absolutely must occur. To put an upper limit on the eventually part, you can define your own range as a cycle-delayed weak sequence. The Property Specification Language does not have a weak eventually property operator. Let's next assert the property that the grant signal is true for only a single contiguous cycle. As we continue to use the same clocking, for our convenience, let's declare it to be the default clocking. As before, we state the assertion, this time without the clocking event, and again postpone the property expression declaration. You have previously seen all of this. We declare the property to take any signal. The property expression is a next cycle implication. The left operand is a sequence. Recall that a signal is a Boolean, which is one kind of sequential extended regular expression, and when braced, becomes a sequence. The right operand is a property. The inversion of a Boolean is obviously also a Boolean, so when braced is a sequence, which is one kind of property. The property expression thus matches the syntax requirements. The property is that if any cycle finds the signal true, then the next cycle finds it false. Let's next assert the property that a grant implies busy, and the busy stays true until and with the done signal. You have previously seen everything that you need to know. As before, we state the assertion and postpone the property expression declaration. Define the property generically as that the first signal implies that the second signal is true and stays true until and with the third signal. Let's next assert the property that arbiter priority rotates in a round-robin manner. How would we express that? We can express that as, if any given device makes a request, then all other devices get at most one grant each before the given device gets its own grant. To write this property generically is interestingly difficult and not practical here, where no grant vector exists. However, it can be done. To write this property non-generically, you have previously seen everything that you need to know. We state the assertion and postpone the property expression declaration. Grant zero fairness is simply that any cycle in which device 0 is making a request and device 1 is getting a grant implies that on the next cycle, the device 1 grant stays low until device 0 gets a grant. You can likewise declare, define, and assert a grant 1 fairness. What is the difference between an assert and a cover? You assert a property. Upon assertion failure, the assimilator reports an error message and sets the error status flag. You cover a sequence. The assimilator counts completions of the sequence. For the cover directive, the assimilator does not issue a message upon failure to complete. For both directives, the Xcelium assimilator counts the number of times an attempt finished, failed, or was disabled. You can optionally also report the checked count. To remember this is important. You frequently describe design behavior by using regular expressions. Design behavior can frequently match more than one expansion of the regular expression. Each attempt on a property can fail, finish, or be disabled only once. Each attempt on a sequence can match multiple times. Let's cover that the devices did a data transfer taking between 1 and 3 cycles. A Property Specification Language directive is an optionally labeled verification directive. Among the defined verification directives is the cover directive. A cover directive is, in order, the cover keyword, the sequence to cover, and an optional report clause reporting a string upon each cover completion. Following this syntax, we label the cover statement, provide a sequence placeholder, and report an appropriate message. The sequence expression syntax accommodates many forms of expression. One of those forms is an instance, potentially parameterized, of a declared and defined sequence. Following this syntax, we instantiate the data 1 to 3 sequence and pass into it the grant 0 signal that starts the sequence. Now let's go ahead to declare and define the sequence. The sequence declaration syntax is, in order, the sequence keyword, a sequence type identifier, an optional formal parameter list, the HDL specific definition symbol, and the sequence expression. Following this syntax, we declare the data 1 to 3 sequence, providing an input argument for the grant signal that starts the sequence. We want to cover that the devices did a data transfer taking between 1 and 3 cycles. How would we express that specification? How about starting with the grant signal, following it by 1 to 3 data-ready signals on any cycles, and done on the last of those 1 to 3 data cycles? You have previously seen that one form of sequence is a braced sequential extended regular expression, and that one form of sequential extended regular expression is concatenation of 2 sequential extended regular expressions. Concatenation means that the left sequential extended regular expression operand completes, and in the next cycle, the right sequential extended regular expression operand commences. We want to express that the done signal is high on the last data cycle. We can do that with the fusion of 2 sequential extended regular expressions. Fusion means that the left sequential extended regular expression operand completes, and in the same cycle, the right sequential extended regular expression operand commences. The sequential extended regular expressions are fused together. Following this syntax, we replace the sequence placeholder with a braced sequence of 3 sequential extended regular expressions. The first 2 sequential extended regular expressions are concatenated, so something happens in the cycle after grant. The last 2 sequential extended regular expressions are fused, so done happens coincidentally with the last cycle of that something. Now, how do we express that 1 to 3 data cycles anytime? One form of sequential extended regular expression is a compound sequential extended regular expression, and one form of compound sequential extended regular expression is a repeated sequential extended regular expression, and several ways exist to express repeated sequential extended regular expressions. The repetition can be in consecutive cycles. Cycles that may or may not be consecutive, thus termed non-consecutive, although consecutive cycles also fit the non-consecutive definition, and a variant of non-consecutive repetition termed go-to repetition. The go-to repetition limits the number of potential matches, which in pure non-consecutive repetition can be infinitely many. So the sequence expression is a cycle with grant true, followed by 1, 2, 3 cycles, not necessarily consecutive, in which the data ready signal is true, and with the done signal true in any of those cycles in which the data ready signal is true. Here, the go-to repetition range creates 3 potential matches for design behavior. The first match is up to the cycle in which data ready is true for the first time. The second match is up to the cycle in which data ready is true for the second time. The third match is up to the cycle in which data ready is true for the third time. The sequential extended regular expression fusion means that done occurs coincidentally with the final data ready, whether that final data ready is the first, second, or third one. Here is the simulation analysis environment, commonly called SimVision, waveform window, displaying in transaction form our assertions and cover. No assertions fail this test. The Xcelium simulator, by default, does not count covers. You enable counting covers by either enabling functional coverage during elaboration or by using the interactive simulator command assertion with its options to turn on covers. The Xcelium simulator, by default, probes assertions and, if enabled, covers as states, that is, active, inactive, finished, failed, or off. You can alternatively probe them as failure events or transactions by selecting the assertions and covers, selecting their menu item Create Probe, and in the Create Probe dialog, selecting either failure events or transactions. Here, the Integrated Metrics Center summarizes the assertion coverage metrics. All sequences and properties completed at least once,